Yay. Hello, everybody. Welcome back to another another wonderful Wednesday seminar. Thank you all for being here. Today, we are looking inwards into the CFA because we actually have two speakers who are at the CFA now, which hasn't happened in some time. So thank you to our speakers for being here. Before we start, a couple of notes. One, we are looking for people to help organize this seminar. All these wonderful talks you see require people setting them up beforehand. So if you want to help us with that, please contact Peter, Federico, or me. Or there is an email address, hi.energy.seminar@cfa.harvard.edu. It's CC'd on all of the notices that go out about this seminar, so you can just email that one. So yes, please come join us. It's a great opportunity to meet new speakers, meet lots of people around, do something for your CFA community and get a lot of visibility as well. So that aside, we will start. While talks are going on, please feel free to put questions in the chat. We can ask them at the end. So if you think of a question in the middle of the talk, don't worry about remembering it at the very end. You can always just write it in the chat and ask it at the end. Or you can wait till the end, whatever you prefer. So without further ado, our first speaker today is Karthik Reddy Solipuram. He is a fifth-year graduate student at the University of Maryland, Baltimore County, and is currently a visiting student here at the CFA. He's primarily interested in understanding the origins of X-ray emission from powerful extragalactic jets, specifically by studying their multi-wavelength morphology with astrostatistical techniques. So Karthik, take it away, please.
All right. All right, thank you. So I'm going to talk about an interesting problem about extragalactic jets. And that is, we don't know how some powerful of these jets produce X-rays. Most of the investigations so far have focused on spectral analysis, but I'll try to give a morphological perspective to what could be happening in them. Marcos and Eileen are my co-authors, and they're also my PhD advisors at UMBC. So we can understand the problem by looking at their ACDs. Now, the radio emission from these jets and optical infrared, if it exists, can be explained by a single synchrotron component, which doesn't predict any detectable level of X-ray emission. But some of these jets are extremely bright in the X-rays. One possible explanation is that there are probably extremely low energy electrons in the jet that emit somewhere here, upscatter the CMB photons to produce these X-rays. This explanation generally requires the jet to be extremely relativistic, even on kiloparsec scales, and also be aligned close to our line of sight. Alternatively, these X-rays could come from synchrotron radiation from a second high energy population of electrons. Now, the problem is that both these models can explain the observed X-ray emission, but they predict large differences in the jet power that gets fed back into the host galaxy. So this is an important parameter in studying galaxy evolution. Now, there are a few problems with the Iccmp model. For example, it predicts large levels of gamma ray flux, which was found to be absent in Fermi observations. The main problem with the synchrotron model is the very existence of the second high energy population of electrons. So we can study their morphology to obtain further clues. So this is a typical image of an X-ray jet with the radio contours overlaid on top. This bright structure is called the core. The intermediate structures in the jet are called knots, and the terminus is called the hotspot. Now, the most common flavor of Iccmp models assume that the radio and X-ray emitting electrons share the same emitting volume, and they are generally unaware of any structure in the jet. And in only a few cases, structure has been involved while interpreting these X-rays via synchrotron mechanism. there is a subtle feature in these jets that needs to be considered. So let's take this knot, for example. If you look closely, the X-rays peak and decay before the radio. Now, this is quite contrary to what one-zone models expect. And so these offsets present themselves as important constraints on the emission mechanism. So we may ask, what exactly are these offsets? What produces them? Can they tell us anything about how knots form, and in turn, how they produce X-rays? Now, before we answer these questions, we need some basic data on these offsets. What are their statistics? Are there any trends in them? So I searched for offsets in a large sample of Chandra detected X-ray jets. Now, detecting and measuring an offset is straightforward. Like, you can take X-ray radio brightness profiles and compare them, or if the jet isn't straight enough, you can simply compute centroid differences. But the problem is there could be interaction with the background, or there could be interaction with the bright core, or there could be emission from the nearby bright knots as well. So a better way would be to deconvolve these observations, which I perform using a statistical tool called Lyra. I won't go into the details here, but in case you are interested, I'll be discussing it more in an upcoming talk. So what Lyra does is that it generates a series of images of the underlying brightness distribution of this image, which we can average to produce a deconvolved image with the effects of background subtracted. Because we have a series of images, we obtain a distribution on the offsets, and we can compute their significance. This is more advantageous in many cases. For example, in this jet, we don't see any kind of structure in the X-rays, and if we just plot a brightness profile in the X-rays, we would see a roughly flat line. But the deconvolved image clearly shows a knotty structure in the jet that roughly coincides with the radio. So I computed offsets in all these knots, and what I find is that in roughly half of these knots, the X-rays peak and decay before the radio, which I indicate with the XF type or the X-ray first type. And in a nearly equal number of knots, I don't find any offset. And in only a few cases, the X-rays appear to extend beyond the radio, but their morphology suggests that those X-rays probably aren't coming from the jet. One problem with claiming co-spatiality is that these knots may have intrinsic offsets in them, but there could be projection effects or distance effects that could reduce these offsets to below a detectable level. So to understand the extent of these effects, I created a categorical parallel coordinates plot. Now, each stripe in this plot represents a group of one or more knots with identical values across these coordinates. CDQs are the core-dominated quasars, which are closely aligned to our line of sight. Lobe-dominated quasars, LDQs, are moderately misaligned, and FR2s are highly misaligned. Now, there is a clear imbalance in this data set, but if you look at the proportions of co-spatial knots, CDQs have the largest of them. And these jets are probably closely aligned to our line of sight, as evident from their superluminal motions in their parsec scale jets. And on top of that, these closely aligned knots also come from larger redshifts. So it's likely that these knots also have offsets in them, but because of limited resolution, we aren't able to detect them. On the other hand, these knots could also be intrinsically different from knots with offsets. So I tested for differences in the distributions of X-ray radio flux ratios between these knots, and I also tested for a difference in the spectral indices, and I couldn't find any. So probably these knots, the co-spatial knots, also have offsets. Next, I deprojected these offsets by assuming some representative angles based on their spectral classes. And to the right, I plot the deprojected offsets for the X-ray first knots based on their classes. Now, the CDQs and LDQs appear to have slightly larger offsets than their misaligned counterparts. I'll get back to that in a moment. But to the left, I plotted all the X-ray first offsets, and I stacked them with the co-spatial knots with a certain threshold. Now, the interesting thing about this plot is that these offsets all have similar value. Most of them have similar values, and then they are also close on the same order as the sizes of knots at low redshifts. Now, at low redshifts, or whenever a knot is resolved in the radio, at least along the jet, it appears extended along the jet, and we don't find evidence for any such extension in the X-rays. Now, this plot is a mixture of resolved and unresolved structures, and the fact that we are seeing similar offsets with them being close to the sizes of knots at low redshifts suggests that irrespective of whether the structure is resolved or not, they they probably have the same underlying morphology and perhaps are produced by the same process. To see why, let's take this knot from a nearby jet called Centaurus A, for example. Now, this is a very low power jet and completely different from the powerful jets that I'm talking about, but it helps to a point about the structure. So this knot has a compact X-ray emitting volume while an extended radio emitting volume. Now, due to some reason, like if we tilt this knot close to a line of sight, or if we move it to a faraway distance, because we may not be able to resolve this radio knot. So we would instead get a point or point-like structure with the peak located at the mean brightness distribution of the resolved knot. And this offset would indicate a lower limit on the size of this knot. So irrespective of whether these knots are resolved or not, if we are seeing same offsets, then it suggests that these knots all have a similar structure: compact emission regions in the X-rays and extended emission regions in the radio. Now, this is a problem for the Iccmp model because there the X-ray emitting electrons have larger lifetimes than their radio emitting counterparts. So we should expect these X-rays to extend beyond the radio, but it would be natural for the synchrotron model because there the lifetimes will be much more smaller than their gigahertz emitting counterparts. So what could possibly produce this structure? Now, based on the frequency independent profiles of these knots in the radio and their near periodic spacing, several authors have suggested that these knots could be separate moving portions of the jet with excess kinetic powers, and these which could be produced by some kind of intermittent activity in the jet. Now, Katauka et al. In a detailed study on a nearby jet called 3C353 slightly modified the suggestion and speculated that these knots are probably heavy moving blobs embedded in a faster outer flow. These knots again would be produced by an intermittent activity in the jet. So this is one knot from the jet. This red dot is the location of the X-rays, and the grayscale image points to the radio knot. So there they speculate that a jet might interact with this knot, producing a reverse shock, which would emit synchrotron radiation in the X-ray wavelengths, and the blob would coincide with the radio. Now, one problem with this explanation is that in several radio polarimetric observations, measurements, the magnetic field doesn't have a radial component, or it aligns with the direction of the jet, which indicates that the radio emission could be coming from a shear-like layer rather than from the entire cross-section of the jet. It can be seen clearly in this knot, particularly if we progressively remove the flux from this knot, we would see an edge-brightened structure, which clearly says that the radio is coming from a surface rather than from a volume. So if we slightly modify this suggestion and say that these blobs act as some kind of obstacles to the flow. So when this flow interacts with this obstacle, it would produce a shock within that flow, which can produce synchrotron X-rays, and those shocked particles could advect downstream, progressively emitting at lower wavelengths while rejoining the flow. So these knots could diffuse into an already existing shear layer, or a shear layer could form while flowing around this obstacle, which can explain this parallel magnetic field nature of the radio. And in an ongoing study in our group, we are finding that the ALMA data has a turnover at millimeter frequencies. That means we require two spectral components even within the low energy part of the spectrum, as opposed to the common belief that just one would be required. So, or in other words, we require one spectral component for the radio and the other for the optical. So it could be that uh, based on the depending on the mass density of this blob, a forward shock could develop and in principle could produce optical emission. So that way we could obtain three spectral components, one for the X-rays, one for the radio, and one for the optical. Now, certainly this is a qualitative explanation and would require further numerical investigations. But if these knots are moving, then to deproject these offsets, we need an additional factor of delta, which is the Doppler boost in the denominator. Now, based on proper motion studies of nearby objects, there is a upper limit on their proper motions, which is about 3 on the bulk Lorentz factor. Now, if I set gamma equals to 3 and use the assumed angles and correct the deprojected values, which is the plot on the bottom row, the offsets are more consistent with each other, and they appear to peak at a value which is much more representative to be a lower limit on the knot size, which are on the order of a few kiloparsecs. Next, I looked at the interknot distances and assumed a Lorentz factor of 3 for these knots, and then I computed what could be the time scale on which these knots could be ejected. This turns out to be about 3 times 10 to the 4 years, which is smaller than the intermittent activity timescales that was estimated in different contexts. One problem could be that we have underestimated the angles, or we are using a much larger value of gamma, but we would again need more data on this one. Beyond one zone models, within the context of a two zone model, within the context of an Iccmp interpretation, there was a suggestion that there could be a faster spine emitting the X-rays enclosed by a slower sheath emitting the radio. So if that is the case, we can test whether the X-ray and radio emitting plasmas reside in different reside in plasmas with different speeds. So to the left is a plot of X-ray luminosities. Sorry about that. This should be CDQs. So I divided the knots into two groups, one with FR2s and LEQs, which contain moderately misaligned to highly misaligned jets, and CDQs which contain highly aligned jets. So clearly there appears to be some kind of distance between these two distributions. Now, if X-ray emission is coming from a faster spine, then this distance should be much larger than what we would observe in the radio if they were coming if the radio was coming from a plasma with smaller bulk Lorentz factors. But the distance appears to be not so high, even if we compute a distance based on a statistical test. Now, there could be, because these luminosities depend on the redshift because of selection effects, I also corrected these luminosities by dividing them with a factor of 1 plus z squared. And even in the corrected distributions, the distances between these luminosities aren't hugely different between X-ray and radio. Yeah. Next, to further look for signatures for Iccmp models, I again looked at the X-ray radio flux ratio distributions, again with the division of FR2 LDQs in one group and CDQs in the other group. So the idea here is that even without a velocity structure, the Iccmp has a beaming pattern where its emission would be amplified much larger than the synchrotron at smaller angles. So that means in principle, we could expect some kind of difference between these two groups, but I couldn't find any difference here. One possibility is that because these knots all have widely different Lorentz factors or boosts or any changes in the internal plasma conditions or magnetic fields, and then that could be reducing any observable difference. And on top of that, the statistical power is too low for the Anderson-Darling test that I've used to test for difference. So we would need more data to confirm or reject whether Iccmp is in place or not. So to conclude, most of these knots have offsets in them, specifically the X-rays peak and decay before the radio. And if we could measure offsets in all of these knots with even more resolution, we could probably detect them. Now, these offsets show that at least the emitting volumes are partially different for the radio and X-ray emitting plasmas, and we cannot use simple one-zone interpretations for these models, for these X-rays. And the fact that we see similar offsets and them being close to the size of knots at lower redshift suggests that they all probably have a similar structure, which is extended regions in the radio and compact regions in the X-rays. And the current data doesn't show any statistically significant evidence for any signatures of Iccmps, and these offsets and their inferred structures suggest that these knots could probably be produced by some kind of obstacles which are produced due to some intermittent activity in the jet, and then and the interaction with the outer jet flow with these obstacles is producing this knotty morphology. Yeah, that's it. Thank you. I'll take questions.
Thank you very much. Great talk. Do we have any questions? You can, yeah, you're getting some applause here. If you have any questions, you can put them in the chat or raise your hand. Yeah, we have a question from Anna.
Hi, thank you for the talk. So just very basic, how much are these offsets in the images in arc seconds?
So the threshold that I've used is 0.15 arc seconds, and it could and then at lower redshift knots it could go until like a few arc seconds.
Okay.
Yep.
Okay, and maybe I missed this, but why is the conclusion that the non-offsets are most likely projection effects instead of the opposite?
These co-spatial knots mostly come from extremely aligned jets, and they also happen to be at much larger redshift than the knots where we find offsets in them. And physically, there is no reason to believe why, just because of projection effects, the structure would vary. So it's probably that they also have offsets in them. We just don't happen to detect them because of a limited resolution.
Okay, thank you.
Yes, we have another question, Aneta.
Oh, let's see. Hi, Karthik. Thanks for the talk. I was wondering about the sample size. So how many knots did you have, and what was the redshift distribution of the knots? I don't think you show that, but that's an important question.
These I considered knots until a redshift of 2.2, and there are about 50 knots distributed, and yeah, it's highly imbalanced. There are only a few knots in the FR2s, but most of the knots come from CDQs.
Okay, And most of them are at redshift lower than 2.5, right? That's right.
Right.
Yeah. Okay.
Yeah.
Thanks.
Mhm.
Thank you. Any other questions? Oh, Aneta, is your hand up again, or is it?
Yeah, I have a follow-up question.
Mhm.
So there is the difference in the volume between the nodes in radio and X-rays, right? So when you calculate the luminosity of the node, there is this difference between the luminosities, right? Because you use this different volumes in radio band and X-ray band. So in some early work, when we were doing the calculations of the luminosities and trying to compare the ratios of the radio and X-ray luminosity in the nodes, we assumed the same volume. And this was something which Dan Harris insisted on doing. But I'm just wondering how much uncertainty is there in the luminosity calculation, which comes from this assumptions about the volumes. Because you use the true volume, right? The radio size and X-ray size, which are different. So I was just wondering.
Yeah. I think we need to change the way we compute luminosities, because I mean, if this obstacle model could be applied to these jets, then definitely X-rays come from much more compact regions than the radio. So yeah, that I in this work I haven't taken that into account. Use the ones with but that can in principle may have a different signature. Yeah, I need to check.
Yeah, it would be nice to look at that.
Yeah.
Thanks. Yeah. Thank you.
Thanks.
Oh, thank you, everyone. I don't see any other questions. So if you do want to continue talking to our speaker, he does have open slots on his meeting schedule today. So please go sign up. Thanks again. And over to you, Peter.
All right, our next speaker is Charles Romero. Charles earned his PhD from the University of Virginia in 2015. He worked with instruments in his next postdoc with Iccmp. He was worked with NICA II and has been involved with Mustang II, handling all of the data that came through, including projects for other PIs. He is currently a postdoc at the CFA since mid-August, and he is working with Ralph Kraft on studies of galaxy clusters, adding X-ray data to SPT analysis. Charles, go ahead when you're ready.
Great, thanks for that introduction. As Peter said, I worked with Mustang II and basically with really one other handled all the data analyses. So some of these papers, projects that I'll be going over are of mine or the team's, but some are other PIs. With that, I'll jump into my talk. Here's an outline. I'll just give an overview of Mustang II, the instrument, where it is. And
Charles, are you sharing your screen? We can't see it, at least I can't.
Thank you. I thought I was, but hopefully everyone can see it now.
Looks great.
Okay, there's the intro slide. So, okay, jumping into the outline. I'll go over Mustang II, quickly talk about motivation for studying galaxy clusters, and then get into the recent results, basically covering 5 recent papers that touch on either SC or SC related science and some conclusions. All right, so first off, Mustang II, it's on the 100-meter Green Bank telescope operating at 90 gigahertz. It has about 30 gigahertz bandwidth, 215 detectors on sky, and most notably on the Green Bank telescope, it achieves 10 arcsecond resolution. It also has slightly over 4 arc minutes instantaneous field of view, a significant improvement over its predecessor. Up on the right corner, I just want to highlight that it really can do whatever science you might be of interest to you at 90 gigahertz, but the dominant projects that get submitted are to study galaxy clusters through the SC effect. And hopefully many of you already know where the Green Bank telescope is, but just to give you an idea, if you didn't know, there's a map in the lower right. All right, so then quickly jumping into motivation for studying galaxy clusters, there are many, a plethora, but one of the principal ones that people will often cite is to constrain cosmological parameters, especially in the sense that you can do this from cluster counts as a function of mass and redshift. So you can get an idea, different cosmologies, different parameters would give you these different, say, curves from a somewhat old paper, but good figure. And from that, you could constrain parameters such as matter constituency and sigma 8. That, of course, depends on, say, what priors you assume, which affect your mass estimates of clusters. Something else to consider just broadly in the game of galaxy cluster surveys is what instruments you're using, namely what frequency are you observing at. Are you observing the ICM, so either SZ or X-ray, or are you observing galaxies, be it just cluster counts? Really, HSC is kind of the only one really doing a reasonable survey and getting weak lensing. That's not true, DES. But yeah, they each have their own strengths. SC has long touted redshift independence to the extent that you're not worried about clusters being really small, far back in redshift. You can see that holds up fairly true. For ACT, they have a fairly indifferent mass cutoff as a function of redshift. Okay, so to get to why use Mustang II, what's the advantage there? If mass estimates are the primary limitation to cosmological constraints, and SC surveys have, say, 1 arc minute resolution or bigger, maybe we're missing something in the ICM and just not getting the full picture, whereas something like 10 arcseconds that Mustang II has could better resolve processes in the ICM. So on the right are images of the bullet cluster, and on the top is as seen with ACT. You see it looks still rather spherical despite rather impressive shocks. Quickly, I think most of you will be quite familiar with the Sunyaev-Zldovich effect, but just to be sure, it's the inverse Compton scattering of CMB. And there are two main constituencies of the SC effect, that being the thermal SC, so just thermal electrons, thermal electron distribution, and you can parameterize the signal strength as Compton Y, given here. Or if your entire cluster is moving along the line of sight, you can have a kinematic SC effect, which is proportional to the velocity and the electron column density. All right. So if mass is the bottleneck and we're hoping to better our cosmological constraints, obviously one of the goals of SC observations will be to derive mass. And how can we do that? So I'll start with, in my opinion, the most intuitive way is to assume hydrostatic equilibrium And this has been done obviously before, starting with X-rays. If you assume that your cluster is roughly in equilibrium and supported by electron pressure, then if you just have also knowledge of gas density, so you do need X-ray data here, you can calculate mass as a function of radius and come up with your canonical masses, say M500, M200. Another twist on assumptions of equilibrium is to assume the virial theorem and then assume a total matter distribution. So an NFW matter profile. This was pioneered by Marchowski 2012, and we'll go on to replicate it shortly here. Or if you rely on some other study that has calculated some mass via one of these methods or another method, and then relates it to some integrated signal for SC, that's an integrated Y, so capital Y, then you can just take that integrated quantity and get a mass that way. So to start off with, we'll look at several mass calculations of Zwicky 3146, a nice, relatively nearby, well-studied cluster, and we'll estimate mass via these different avenues. And you see here are some literature mass estimates already. And then we fill in with now 5 different estimates. So 3 of them will be from YM relations, since there are several YM relations to choose from. There's a hydrostatic equilibrium estimate here, and then the virial theorem estimate there. And I think a more interesting way to look at this is, are you getting your mass estimates effectively from assuming hydrostatic equilibrium, even if, right, your YM relation could be essentially based on hydrostatic equilibrium, or it could be based on weak lensing or numerical simulations. And so you see this division. Most of the hydrostatic equilibrium estimates are coming in below, in particular, this last weak lensing estimate. There were certainly some difficulties getting the virial theorem to fit nicely, but that's fine. I'm not sure it's the one we should prefer anyways. And specifically, if you just look at the explicit hydrostatic equilibrium mass, we would infer a hydrostatic mass bias of 0.07. So overall, this cluster, Zwicky 3146, seems to be quite well supported or dominated by thermal pressure, where, just to be sure everyone, if you don't have some expectation, mass biases are expected to be roughly between 0.1 and 0.3. All right. So let's take that approach of getting masses from Mustang II data, and we'll apply it to a sample of clusters. In particular, we'll go on to the mad cow sample that's been observed with Mustang II. So mad cows obviously is stemming from WISE, at least their initial candidates are from that survey, but then they'll add on other telescopes to get better cluster richnesses. Despite having richness mass relations, they want also ICM derived masses, which they expect to be, I'd say, a bit better. Here are just a sample of 3 of the clusters in, I think, 16 we used. Surface brightness profiles, I didn't go into it with Zwicky 3146, but ultimately we'll recover electron pressure profiles shown on the right. and then we'll infer a mass from that. In particular, for this study, the masses end up being derived assuming the YM relation from Arnaud 2010. So what do we end up getting? We calculate our masses are in blue here, and we can compare to some of the masses inferred in some previous Mad Cows papers, especially those published, say, from Gonzalez 2019. And you see that our masses generally fall below what they expect, especially if you use their scaling relation, which is off of Karma SC and I believe weak lensing. There are certainly many possible culprits for this discrepancy. We are a bit less scrupulous to weed out some of the clusters that we didn't detect. They did weed out more clusters. Additionally, we think that the fact that some of these clusters look, say, elongated or otherwise suggestive of being dynamically disturbed, that perhaps the YM relation we're employing isn't the most appropriate. Or, I mean, it could equally be suggestive that the cluster richness relation also has room to improve. All right, so going beyond just deriving masses from SC data, another paper that came out is Okabe 2021, where they observed 3 galaxy clusters initially observed with the Subaru Hyper Subprime camera. It additionally had X-ray data with it, or these clusters in particular. And so we already have the mass estimates from weak lensing effectively, or in the paper they go through that. But then we'll be able to figure out a bit more about the dynamics of these clusters. And let me also highlight this plot on the left. It's just showing, again, distribution of clusters from different surveys, and then in particular, where these clusters that are in this study lie, the black stars. So again, Mad Cows was generally quite high redshift. Zwicky 3146 was on the lower redshift of clusters studied with Mustang II. Okay, so you can do canonical profile analyses. Here are shown just simplistic spherical profiles for one centroid, even though for clusters such as cluster B, where there are 2 peaks, the analysis is also done on those 2 peaks for all 3 data sets. And to kind of jump to one of the bigger conclusions, at least especially from an SC background, thinking about how does your integrated Y compare to a mass estimate, you see that the merging cluster, which is shown basically 6 different ways here. There's an Eastern, a Western component, and a total component. And then they also do some analysis with X-ray temperatures, allowing for a hot component and total hot and cold component. You see that the mass estimates vary in each case. Whereas the other 2 clusters that don't have double peaks are much closer to a YM relation. So obviously, treatment of merging clusters is not so straightforward, and I'm not sure that there's yet a simple solution of what to do there. In terms of interpretation of dynamics in these clusters observed, I think it was quite interesting to find rather hot gas temperatures in the outskirts of that merging cluster, cluster B, 20 or 28 kiloelectron volts. And those temperatures would not have been revealed by Iccmp data alone. In terms of cluster A, if you look at the galaxy distributions and then also the residuals after you subtract a bulk component, the interpretation is suggestive of it being in a sloshing phase. They also looked at numerical simulations from John Zuhone and found that that was in agreement with those simulations. And then cluster C exhibits elongation in the SC and X-ray, and that combined with centroid and BCG offset would suggest that it's in a pre-minor merger state.
3 minutes left.
Thank you. All right, so 2 more papers to try to get through. This next one will be our highest redshift cluster observed to date with Mustang II. It's IDCS 1426 at redshift 1.75. And at that point, I'd say the interest is not so much getting our own mass estimate, but just understanding evolution of thermodynamic profiles, especially in the context that often a universal pressure profile is assumed. And should we really be going about assuming that? Let's see, I will go quicker through this. We looked at profiles both individually in the SC and X-ray, but then when you combine them, you get rather nice constraints on each of these thermodynamic quantities. And I would also highlight the time spent on SC and X-ray are given there, and that we find this is actually quite an effective use of total instrument time if you compare to other studies where you observe for, say, 170 kiloseconds of just Chandra. I think we still come out ahead by splitting it up. All right, and then to actually understand the evolution of these thermodynamic profiles, we take our derived profile and compare it to roughly z equals 0 profiles, especially those determined by the Iccmp sample, so Uradini 2019. And we calculate these evolutionary rates, with respect to physical radius rather than scaled radius, so as to avoid what the author calls pseudo-evolution, right? Even if you don't accrete any mass, just the fact that the critical density is decreasing over time would change your R500. And so even though scaling relations or self-similar evolution is useful and expected, it also is good to think of it in terms of physical radius. And to get a better handle of what our expectations should be, we compare these results to numerical simulations. And so the big takeaways really are that the temperature and entropy excess at large radii are kind of the unexpected features that ultimately have to shift elsewhere, really inwards into the cluster with time. Whereas even though pressure was in excess relative to expectation at z equals 1.75, the pressure will, with time, actually increase even at 500 kiloparsecs. And of course, once one cluster is really not sufficient to say too much about evolution of clusters over time, so we need to study more clusters at high redshifts. And the final study I want to touch on is point sources even though Mustang II has really a heterogeneous sample of clusters studied, it's upwards of 30 clusters now, and we can start to comment on how prolific point sources are and how much they would affect, well, not too much our observations since we have the resolution to pick them out, but say SC surveys. And in particular, we take a look to ACT, which uses a matched filter to get their cluster catalogs and ultimately get a mass estimate. That match filter basically is working on scales of 2.4 arc minutes. And so a little outside 100 arc seconds. What's kind of interesting with that match filter is the contribution of point sources will actually be positive to their central Compton Y that they use. So in fact, where infill is the standard concern, you actually have the other concern as well, that you're adding to a cluster strength. So quickly, quite a few plots to go over. The dependence of the effect on that central Compton Y will depend a bit on, well, I guess the redshift of the cluster, but also spectral index and the flux itself at a baseline frequency, which for this study was 90 gigahertz, Mustang II. You see that for an assumed spectral index of minus 0.68, that roughly matches what we have on the infill side, but on the positive side, it's overestimating what we actually see with Mustang II. Another big takeaway is that the impact of point sources is a bit skewed for an SC survey relative to what you would get from an X-ray or optical survey, where point sources aren't really impacting its selection function, and therefore you get more of an impact of point sources from those surveys. And ultimately, where a lot of studies have used lower frequency radio data and extrapolated to SC frequencies, we hope that this study motivates other studies to look at point sources at SC frequencies. Okay, quickly, conclusions and forward. I think Mustang II obvious strengths should be its 10 arc second resolution. This enables many things: point source detection and removal, resolved pressure profiles, and in turn, mass estimates, not relying on a specific profile shape. Also, we do excellent at looking at the low density outskirts of clusters. And in the future, we're hoping to look not just at your standard pressure profiles, but really interesting features in the ICM, say shocks or X-ray cavities. In fact, here's some Mustang II data on a very famous cluster. And of course, our SC data is highly compatible with X-ray and weak lensing data. So with that, I'll wrap up.
Thank you, Charles, for a great talk. We are running late, but if folks want to stick around, we have time for a couple of questions. So either raise your hand in the participants window, or if you want to type something out in the chat, we'll be happy to read it for you. All right, if there are no questions right now, then if you'd like to talk to Charles later, please sign up on his meeting spreadsheet. And let's thank both of our speakers for another great couple of high energy talks, and hope to see you all next week.